Hello everyone, welcome to this session on Poisson distribution. My name is Vamsidhar. As a part of the session, I'm going to talk about the basic introduction to the Poisson distribution. What is the distribution function? So in the introduction, I would also talk about what are the typical applications, where do you use the Poisson distribution, then how do I compute the mean of a Poisson distributed variable and the variance. And suppose I have a Poisson distribution problem, what is the strategy to solve that? And then I talk about two different Poisson distributed variables, x and y. So if I want to find out the distribution of x plus y, so x is a separate Poisson distribution, y is a separate Poisson distribution. Then I want to find out the distribution of x and y, x plus y. How do I really build it in the form of Poisson distribution? And finally, how does a binomial distribution approximate to a Poisson distribution? These are some of the things that I am going to look at in this video. So let me get started. So whenever you are using Poisson distribution, the major thing is we are using it to model random events. So an event that is occurring in a random fashion. It could be a random event with respect to time. Let's say telephone calls. You receive telephone calls on a random basis. You don't know when you will receive one call. So that is what is a random event with respect to time. In some cases, a random event could be with respect to a space itself. In a particular area, in a particular book, right? In a particular book, a particular page getting torn. Randomly, one page is getting torn. Or in a particular book, one page is misprinted, wrongly printed. So these are the examples of randomness with respect to space. So generally, I would be interested in modeling random events either with respect to time or with respect to space. So whenever we are trying to model this random event using a Poisson distribution, we have a parameter. A Poisson distribution uses a parameter called lambda, right? So we say x, which is a random variable, it follows a kind of a Poisson distribution with a parameter lambda. So this is how we mathematically model it. We say a random variable x follows a Poisson distribution with a parameter lambda. Any distribution is nothing but it's a frequency distribution, a shape, right? So when I say x follows a Poisson distribution with a parameter lambda, some of the important conditions that are necessary are the events that are occurring, they should be occurring randomly. So the telephone calls that I am going to get, they occur randomly, they cannot be timed. So in that case only I can use the Poisson distribution. The events that are going to occur, they should occur randomly and they should occur independently. So it is not like if the first phone call has come, the second is going to come immediately. So I can't predict the pattern. So that is where we are saying independently. If the first phone call has come now, we don't know when the second is going to come. So the occurrence of the first one does not say that the second one is going to happen immediately. So that is what we mean by independent occurrence. And two events cannot occur simultaneously. Obviously, if I get one phone call, the second cannot come, because obviously if one is coming, I would be servicing the one, so the second one has to wait. So that is where we are saying the events, two events cannot occur simultaneously. And over the entire time that we are talking of, at any point in time, if I am talking about a day, at any point in time, there should be a constant probability of occurrence of that event. So it's not that I will get more calls in the morning or I will get lesser calls in the evening. That is not what we are saying. The probability of occurrence of that event is constant across the entire space. When these four important conditions are met, that particular random event can be modeled using a Poisson distribution. So the most important point is, only when these four important conditions, one event should be random, they should occur independently, two events cannot occur simultaneously, and there is a constant probability of occurrence of the event over the entire time or space. So now coming to the equation or the mathematical formation of this Poisson distribution. So if I am talking about x, which is talking about the number of random events, that is how the Poisson distribution is modeled. So when I talk about x as the number of random events in a particular time, so I am trying, so the mathematical part is, I want to understand the number of phone calls. Here the random event I am talking about is a phone call. So the number of random events occurring in a particular period of time or space, book, the number of misprints occurring in a book of 500 pages. So that is what I am calling as x. That is what is a random event. I am trying to find out the number of events that are occurring in a particular period of time. Right? In that, the lambda, which we called as a parameter, is the mean number of occurrences in that particular interval. So if I say lambda is 10 per day, so on an average I am receiving 10 calls per day. I don't know when I am going to receive, but on an average I am receiving 10 calls per day, and x is the number of random event, number of phone calls with an average of around 10 per day. And if x is following a Poisson distribution, x will follow a Poisson distribution when these conditions are met. So if x follows a Poisson distribution, then the probability of x equal to some value x is given by e to the power minus lambda, lambda power x divided by x factorial, where we are saying x is taking values 0, 1, 2, so on. So this is what we typically call as the probability distribution function. So this is how the probability is distributed. So if I am saying that X is the number of random events, number of phone calls that occur in a particular time period, lambda, if I take it as the mean number of occurrences of that event during that time period, and if I know X follows a Poisson distribution, then the probability distribution function is typically obtained through this particular expression. Probability of X equal to X is equal to e to the power of minus lambda, lambda power X divided by X factorial. Alright. And here, if the random events are occurring in a continuous time space, obviously it can occur any second, any minute. So if these random events occur in a continuous time space, time or space kind of, so everything is continuous, then that kind of processes we call as Poisson processes. So this is the first important part that you need to be comfortable with. So the number of telephone calls you receive probably during an hour period. So in a particular time or in a particular space, you have to always talk about that particular aspect when we talk about a Poisson distribution. So let me just give a quick example. So if I am saying that the telephone calls, right, telephone calls I receive at a mean rate of 23 per day. I am receiving around 23 telephone calls per day. And I found that X is following a kind of a Poisson distribution. So the parameter is also lambda out here. Find the probability that in a particular day, I get exactly 20 phone calls. What is the probability that in a particular day I get exactly 20 phone calls? Or find out exactly what is the probability that I get anywhere between 21 and 23 phone calls per day. So this is how I can really use the Poisson distribution, because if I really want what is the probability of getting 20 phone calls per day, we can directly use our formula e to the power of minus lambda, lambda power X divided by X factorial. Right? So if you really want to find out this probability, you can use either a spreadsheet or a calculator or whatever. So here it is being said that lambda is 23, X equal to 20. So I can very well find out the probability of X equal to 20, which is nothing but e to the power of minus lambda times lambda power X divided by X factorial. So this is saying exactly 20 phone calls in a day, the probability is around 7.23%. Now the same way, if I really want to find out what is the probability that I get 0, 1, 2, 3, so on, I can put it in a spreadsheet, right? probably if I am interested in finding out what is the probability that I get, let's say up to 50 phone calls per day, 0 to 50 phone calls per day going with this. So I can very well put e to the power of minus lambda into lambda to the power x divided by x factorial. So you could see that getting 0 phone calls is almost negligible. Probably if you want you can convert it into percentage, and I could see if I am summing it up overall it is coming out to 100%. So I could see that, and if I typically try to plot the graph of this, so here it is coming out more or less a kind of a bell curve. Majority of the probability is around 20 to 23 kind of a percent. After that it is falling, and before that also it was like a fall. So that is how the Poisson distribution can very well be looked at, especially. So you have to understand in which context you should be using the Poisson distribution. So if someone has asked us what is the probability that the number of calls is between 21 and 23, I can simply add up these three and I can say it's around 24.5%, right? So depending on, once you have created a kind of a quick model, you can very well use this information for finding out the probabilities of any kind of combination. Now look at this one. So let me simplify instead of, okay, let's keep it like this. Now for this, right, this is how we understand the probability distribution function. And now for this, let's say I want to find out the important properties, the mean and the variance. There are two important things for any such kind of distributions that we should be interested in: the mean and the variance. So if I typically look at it, the mean is, let's take our spreadsheet only. So mean is nothing but I take the weighted average of all these things. So if I really want, it is nothing but 0 into 0.000% plus 1 into 0.000% plus 2 into this. So it's a kind of a weighted average. So in Excel I use the typical sum product, where this is my first array and typically this is my second array. So I do a kind of a pairwise multiplication and addition, which is giving me that my mean is approximately 23. I got it, even if I round it up, it comes out to 23, right? So which means if I talk about a Poisson distribution, the general way to remember is, in a Poisson distribution the mean is nothing but it is lambda. Lambda itself is the mean. Now the same way, if I really want to find out the variance, if you remember any kind of data distribution, variance is nothing but expected value of x squared minus expected value of x whole squared. Expected value of x squared is nothing but I square this, right? I square this and then find out the sum product. So expected value of x squared, if I have to find out, which is nothing but I multiply the probabilities with the expected value of x squared with the x squared values. Alright. So this is what I got, expected value of x squared. So the variance is nothing but expected value of x squared minus expected value of x whole squared. So in this case also it started coming out that the variance is also 23 in this case. Right? The mean is 23, variance is also 23. So this is one special property of a Poisson distribution. A Poisson distribution is something which has a mean and variance, both of them as lambdas. Right? So we have seen through the example, and you can also try it through some kind of a derivation also. Just giving you expected value of x is nothing but, so when once you know the probability distribution function, this is your probability distribution function. So expected value always is nothing but you multiply it with x and do this, and you sum it over the entire values of x from 0 to infinity. So this is what will lead you to lambda, and once you know that this expected value of x is lambda, variance of x is nothing but, as I have already told you, expected value of x squared minus expected value of x whole squared, which also will lead you to the same lambda. So you can very well do it from the numericals, or again, if you are interested in the proofs, you can refer to any kind of a good statistics based textbook as well. So these are some of the basic concepts that I want you to be comfortable with. So any time now, if you are given any kind of a numerical problem involving a Poisson distribution, some of the important things that I want you to look at is, first of all, see whether the rules which we discussed initially, the conditions, only in those cases the Poisson distribution is applicable. Many a time people make mistakes in terms of understanding whether the Poisson distribution is applicable to that problem or not. So the initial four conditions that we have discussed, that the event should occur randomly, they should occur independently, both of the two events cannot occur simultaneously, and the probability of occurrence of an event should be constant during the time period. And after that, so try to understand what is the lambda for that particular problem, and then write the distribution function based on the value of lambda. And after that, as I told you, as I have given you a kind of a spreadsheet or a calculator, try finding out what is the probability of x equal to x for different values of x, and if required, find out the mean and the variance. We know that the mean and the variance, both of them are lambda only. So variance is lambda, means standard deviation is always the square root of variance. So I'll take it as square root of lambda. Right? Now, slightly a different one. So I'm talking about, till now I have talked about one single time interval t. During this period, I said lambda number of, on an average, lambda number of phone calls occur during this particular time period, or even in a space. In a book of 500 pages, on an average 4 pages are misprinted, which is lambda number of pages are misprinted. But if I am talking about not just one day, but similarly I have 5 days, right? So which is here my time interval is, I'm having equal time interval. So there are 5 different T's. All my time intervals are equal, and in each case, let's say it's a lambda, then I can very well do the summation also. So if I really want to find out the total number of random events, that are occurring over this 5 periods is nothing but I can do a simple summation of the number of events that are occurring in each of the intervals. So look at it like this. If I am talking about xi, where there are n different independent and identically distributed random variables, and they are following a Poisson distribution with the parameter lambda, which means the mean is also lambda. So if I am talking about the summation across the entire set of values, and if I am saying that xt is the summation also will follow a Poisson distribution, but it will have a mean of n lambda. So in this case, it will have a mean of 5 lambda. If I am talking about the number of random events occurring in this 5t time period, I can very well say it also follows a Poisson distribution with a parameter 5 lambda. So let's take an example to understand it. So if I am talking about I say let me take lambda equal to 5, right? Let me take lambda equal to 5. This is per hour. I get 5 phone calls per hour. So what is the probability? It follows a kind of a Poisson distribution. What is the probability that I would be getting 14 phone calls in 3 hours? Right? So this is where I can apply this summation. So I am talking about lambda of 5 per hour, which is also same as 15 per 3 hours. This is how I will write it. So my lambda is nothing but 15 per a 3-hour period. So if I am talking about the probability of x equal to 14 in 3 hours, e to the power of minus lambda, lambda to the power x by x factorial. So this is one more additional thing that you need to be comfortable with. Anytime we are talking about time period wise equal time intervals, if I really have to extend it by multiplying or reduce it by dividing, I can very well take my proportionate lambda accordingly. That is one more property of a Poisson distribution. And even if the lambdas are different, right? Even if the lambdas are different, let's say I am talking about two companies X1 and X2. X1 is getting calls, let's say following a Poisson distribution with a lambda of 10 per day, and X2 is getting calls at the rate of 15 per day, right? So the lambda 1 is 10, lambda 2 is 50. So there are two different lambdas altogether. But still, if I am trying to understand what is the probability that the total number of phone calls that both the companies together get is more than 30 per day. What is the probability that both the companies together get more than 30 phone calls per day? So in this case, I create lambda as the summation of both the individual lambdas, making it 25 per day. On an average, both the companies put together, they should get around 25 phone calls per day, because both of them are per day. So the probability that lambda is greater than 30 is nothing but 31, 32, so on. So I can very well find out the either up to 30 I find out. So I can very well say what is the probability here. If I change 30, I could very well find out what is the probability of 0, 1, 2, so on. So based on this, I can very well find out what is the probability of less than 30. So this is the probability of less than 30, which is around 54.83%. So greater than 30 will be the remaining part of it, which is 45 point something. So this summative property that we have brought out, one of the important properties in case of a Poisson distribution, even if the means are different, even if the parameters are different. So to generalize this, I am talking about x and y. So x is one random variable with a parameter, let's say lambda. Y is another random variable with a parameter mu. And then I want to find out the total. What is the distribution of this total x plus y? I can very well say that this also follows a Poisson distribution with parameters lambda plus mu. Right? So the same example where I said, okay, x follows a Poisson distribution with a parameter 10, y follows a Poisson with a parameter 15, and then we said these are per day. So my question can very well go to what is the probability that there will not be more than 200 phone calls per week for both the companies put together. What is the probability that the number of phone calls per week is less than 200? Again the same logic. So per day I say it is 25. So per week, so my lambda, which would be a new lambda, is nothing but 25 per day, or it is 175 per week. So my new lambda will be 175 per week. But this kind of approximation can be done only when the initial 4 rules are getting met. So we always have to keep checking whether the 4 rules are getting met. Solving these numericals is not a big difficulty, but trying to ensure that the rules are typically being met is what an important aspect of the understanding and modeling of the Poisson distribution. And finally, Poisson distribution is a kind of an approximation of a binomial distribution, because if you remember the binomial distribution, we talk about number of events. So when we say a particular experiment has been performed n number of times, with each probability of success being p and the probability of failure being the q, 1 minus p, it says the probability that there are n successes or x number of successes we take it as ncx, p to the power x, q to the power n minus x. This is what used to be the probability distribution function associated with a binomial distribution. Now if I am assuming that the number of events is similar to the number of pages in a book or the number of minutes in a time interval. So if n is very high and the probability of occurrence of the event is very low, right? The number of events that are occurring is very high. The probability of occurrence of that event is very low. I see that whatever is the probability that we get through a binomial distribution, the same can be done using a Poisson distribution, where you take the lambda as nothing but the whatever the number of successes that you are getting, x divided by the number of times that particular event is being conducted. You take the lambda as x by n, and your Poisson distribution can very well be approximated, or binomial distribution can very well be approximated to a Poisson distribution. So if x is having a kind of a binomial distribution with n being the number of trials and p being the probability of success, n is very large and p is very small. So you can very well approximate the same to a Poisson distribution which is having a parameter of np. So the lambda you can take it very well as np, and both of them should give you a similar kind of a result. So the larger the value of n and smaller the value of p, I can very well approximate a binomial distribution to a Poisson distribution. So these are some of the things which I thought I should cover as a part of this session. I hope you got a good amount of decent understanding about the Poisson distribution and the various basic concepts regarding the Poisson distribution. If you have any further queries, you can very well mail up at the email address that I have given below. Thanks a lot for listening to this session. Thank you very much.